Are we alone in the universe? It's such a fundamental question, isn't it?
It really is.
And today we're doing a deep dive into something pretty concrete that might, just might, hold a piece of the answer. We're talking about rocks. Rocks collected on Mars.
Yeah, and it's fascinating just to, picture Mars. Today, it's this cold, barren place.
Right. Desolate.
But the science, well, it overwhelmingly points to a very different past, billions of years ago. Probably warmer, probably had significant water, lakes, maybe rivers.
Environments where life as we understand it, could potentially have gotten started.
Exactly.
Yeah.
Which brings us to Perseverance in Jezero Crater.
Right. Since 2021, the rover's been up there doing more than just taking pictures. It's been carefully drilling and collecting rock samples.
Uh-huh. And the mission is really twofold. One, look for signs of that possible ancient life.
And two,
Figure out why Mars changed so dramatically. Why did it lose that potentially habitable environment?
and the crucial part is, these samples aren't just staying on Mars. There's this whole ambitious plan, the Mars Sample Return Mission.
That's the key. Getting them back here. Planetary scientist Meenakshi Wadhwa said something really insightful about this.
Oh, yeah?
She said, every single one of the samples on board the rover has the potential to answer one or more of our most important questions about Mars. It really puts it into perspective.
It does. And, I mean, we have looked at Martian rocks before, haven't we? Curiosity found sulfur, which was interesting chemically.
Absolutely. That was important data.
Yeah.
But these Perseverance samples, they're different because they've been specifically chosen from areas that look, geologically speaking, really promising for preserving signs of life. It could be a turning point.
Okay, so that's our mission for this deep dive then. Let's get into what specific kinds of rocks Perseverance has grabbed and, what secrets they might be holding.
Right. What can they tell us about past life, about how Mars evolved?
Let's start with Jezero Crater itself. Why there? What was so special about that landing site?
Okay, Jezero. The big draw was the evidence, seen from orbit, that it used to be a lake fed by a river. Over 3 billion years ago.
A river delta, basically.
Precisely. An ancient river delta flowing into a lake. And on Earth, deltas are often fantastic places for organic material to accumulate and get preserved. Think ancient river mud.
So the hope was, find that ancient lakebed mud, maybe something really rich in organics. I think I heard Branny Horgan call it the gooeyest mud, something like that.
Yeah, that was the idea. Go where the mud was, because that's often where the biological evidence gets trapped and preserved on Earth.
And did they find it? Was it just sitting there?
Well, interestingly, the surface looked quite sandy at first. But when Perseverance started drilling, they found these muddy horizons underneath those sandy, kind of salty layers, like layers of old mud, basically sealed off.
And that's significant because, like you said, on Earth, dried mud can be amazing for preservation.
It really can. On Earth, you find incredibly detailed preservation in ancient dried muds, organic molecules, even fossilized microbes sometimes.
Mm-hmm. So finding that same type of deposit on Mars in a former lakebed, that's exciting.
Hugely exciting. It means we found the right kind of place where biosignatures could be preserved if they were ever there.
But that's the million-dollar question, isn't it? Whether anything is actually in that Martian mud.
That is precisely the question. We had the right rocks, the right environment. But did life exist, and did it leave a trace? We won't know for sure until those samples are back here.
Okay, but Perseverance didn't just sample the delta mud. What about the rocks from the crater floor itself? Those were some of the first ones collected, right?
Yes, those first crater floor samples are critical for dating. We need to pin down when Jezero Crater formed, and importantly, when that lake and delta were active.
And the current estimates are pretty broad.
Very broad. Plus or minus 500 million years. I mean, that's a huge amount of uncertainty when you're trying to piece together a planet's history.
So getting a precise age from those floor rocks helps calibrate everything else that happened in Jezero.
Exactly. Knowing the context where they came from and getting a solid date is invaluable. Sandra Holstrom mentioned this, that a big part of the dating problem on Mars is just not having enough datable rocks with a known origin story. These samples help fix that.
And these floor rocks, they were igneous, right, from lava flows. What else can they tell us besides just the age?
Right, igneous rocks. As Meenakshi Wadhwa pointed out, they're like little probes into Mars's interior. Their chemistry tells us about the mantle, the deep composition of Mars.
And why is that important?
Because it could hold clues about why Mars lost its global magnetic field way back when.
The magnetic field, which protected the atmosphere.
Exactly. Losing that field was probably a key step towards Mars becoming the cold, dry planet we see today. Understanding the interior helps understand that massive change.
Okay, let's shift gears a bit. There was another sample location that got a catchy nickname, the bathtub ring. What's that about?
Yeah, the bathtub ring. It comes from orbital images. Scientists saw these deposits of carbonate minerals sort of ringing parts of the Jezero Crater rim.
Like the ring left in a tub after the water drains.
Pretty much. Brainy Horgan used that analogy. Carbonates are minerals with carbon and oxygen, often formed in contact with water.
So the idea is this was maybe an ancient shoreline.
That's the leading hypothesis, yeah. Maybe the edge of a shallow lake. Could have been freshwater, maybe alkaline. Carbon is precipitated out of water in those kinds of settings on Earth.
And are carbonates common on Mars?
Actually, no. They're relatively rare on the surface overall. But seeing them concentrated here in this ancient delta system makes Jezero even more interesting.
And what do carbonates tell us beyond just water was here?
Well, as Bryony Horgan noted, they're excellent environmental indicators. Their specific chemistry can tell you about the water chemistry at the time, maybe the temperature, even hint at atmospheric conditions. They're like little climate records.
Did Perseverance grab samples from this ring?
It did. 3 samples from what they call the margin carbonate unit. 2 are sedimentary likely layered sediments.
Okay.
And 1 is a silica cemented carbonate. So silica acting like a glue.
And what could those reveal?
Meenakshi Wadhwa suggested the sedimentary ones especially could show the range of watery environments that might have existed there. Different conditions, maybe different times.
Fascinating. Now, there's one sample that seems to have generated quite a bit of buzz, Ch'ał'ee'vil Falls. Tell us about that one.
Yes, Ch'ał'ee'vil Falls. Collected July 2024. This one's exciting because the rock itself clearly interacted with flowing water. But the really eye-catching thing, these features they called leopard spots in the Rover images.
Leopard spots. Okay, intriguing. What are they supposed to be?
They look like evidence of chemical processes happening within the rock, driven by water. And the key thing is, on Earth, similar chemical reactions can actually be used by microbes as an energy source.
So the spots suggest conditions that could have supported life.
Potentially, yes. It points to an environment with the right kind of chemistry.
And wasn't there something else about organics with this sample, too?
That's right. Strong evidence for organic molecules in the Ch'ał'ee'vil sample as well. The building blocks of life. And Sandra Siljeström pointed out, it's a very fine-grained rock. Those types are often really good at trapping and preserving biosignatures. Any kind of evidence, physical or chemical, left by life.
Okay, but we need the big caveat here, right? Finding organics in interesting spots doesn't automatically equal finding Martian fossils.
Absolute crucial point, yes. It's incredibly promising, very suggestive. But there could be non-biological ways these things formed. We need to get these samples back to Earth labs for the definitive tests. No way around it.
It's amazing to think about the rover's journey. Landing on the floor in early 2021, exploring the delta, and then actually climbing up the crater wall.
It's been quite a trek. Reaching the top of the rim in December 2024 was a major milestone. That's a serious climb for a rover.
And it kept sampling even up there.
Yep. January 2025, it grabbed the first sample from the rim itself, nicknamed Silver Mountain.
And the thinking is, rim rocks are older.
Generally, yes. Rocks higher up on a crater rim often represent older geological layers. Sandra Siljeström highlighted this. Silver Mountain is likely the oldest sample collected so far.
And why is older potentially better for finding life signs?
Because the further back you go in Mars history, the more evidence we have for liquid water being around. So the thinking is maybe Mars was more habitable way back then.
Makes sense. So where we stand now with the sample collection, how many tubes are filled?
Okay, the latest count is 21 tubes sealed up and stored inside Perseverance. That number includes 2 witness tubes.
Witness tubes, what are those?
They're basically controls. Empty tubes open to the Martian air in the sampling system, then sealed. They help scientists figure out if any Earth contamination got onto the real samples.
Smart. And how many tubes does it have left?
It still has 8 regular sample tubes and 2 more witness tubes available. So the collection isn't over yet.
All this effort, the careful sealing, the witness tubes, it really drives home why bringing them back is so important. Why can't the rover just analyze everything there? It has fancy instruments.
It does have great instruments. But as Meenakshi Wadhwa explained, there are just fundamental limits to what you can do remotely with a robot. We'll think about lab equipment here on Earth, the power, the size, the variety. You can do incredibly precise radioisotope dating to get exact ages, something the rover can't really do. You can examine rock textures under powerful microscopes, analyze mineralogy in minute detail, look for complex organic structures, things that are just impossible to miniaturize onto a rover.
So the labs here can just do much, much more detailed work.
Orders of magnitude more. There's no substitute for getting them back here.
Okay, so when might that actually happen? When do we get to, get our hands on these rocks?
Patience is key here. The Mars sample return mission is incredibly complex. Multiple spacecraft, robotic transfers in orbit.
Right.
It's ambitious stuff.
Right.
The current best estimates point to maybe the mid-2030s at the earliest.
Mid-2030s. Wow. Okay. It feels like a long time, but I guess for questions this big.
Exactly. And think about the Apollo moon rocks.
Yeah.
We brought those back decades ago, and scientists are still studying them, still making new discoveries with new techniques.
That's a great point.
Bryony Horgan made that comparison too. She sees these Mars samples as like a legacy, a scientific treasure trove for future generations to study for potentially centuries.
So wrapping this up, Perseverance has collected this amazing variety pack, essentially. Muddy delta sediments, ancient volcanic rocks from the floor, those interesting carbonates from the rim, and then Ch'ał'ee'vil Falls with its tantalizing chemical hints.
Precisely. Each sample type is a different piece of the puzzle. A window into Mars's past environment, its geology, and maybe, just maybe, evidence of past life.
Which brings us right back to where we started. Are we alone? Could the answer, or at least a huge clue, be sitting in one of those little metal tubes waiting to come home?
It's the driving question. This deep dive really shows the incredible potential locked away in these rocks. The journey of discovery won't even end when they get back to Earth. It'll just be starting a new chapter. It really makes you think, doesn't it? What if we do find something definitive? What does that mean for everything we thought we knew about life in the cosmos?